Good evening and welcome into the Science Files. I'm Madeline Rowe, and tonight we're going to follow the evidence behind one of Earth's largest geological riddles. How does a volcano become powerful enough to erase its own mountain? We'll follow the evidence behind the largest explosive eruptions the planet can produce, beginning with the word itself, then moving through ash deposits, collapsed calderas, magma reservoirs, zircon crystals, seismic instruments, and the strange climate record left behind when sulfur rises into the stratosphere. And if you enjoy these calm, evidence-backed case files, please subscribe, and there'll be another one waiting for you soon. There are volcanoes that announce themselves with a cone on the horizon, a summit, a plume, a crater edged against the sky. They fit the shape the human mind expects, a mountain with fire inside it. But some of Earth's largest eruptions do something more difficult to picture. They remove the mountain from the story. They empty so much magma from beneath the ground that the roof of the volcanic system fails, and the surface falls inward. What remains may look less like a volcano than a basin, a lake, a plateau, a park, a ring of hills, a broad depression written into the crust so gradually that a traveller can cross it without knowing they have entered the outline of an old catastrophe. That is the first difficulty in this file. The largest volcanoes are not always the most visible. Sometimes the evidence is spread too widely to fit into a single view. Ash lies far from the vent. Welded tuff hardens into cliffs. Fine glass shards settle into lake mud. Crystals no wider than dust grains keep time in their interiors. The volcano itself becomes a negative space, a place where the ground once lost support and sank. Back in my office, the lamp over my desk casts a pale circle across a folder stamped with 3 lines of surviving metadata. Supervolcanoes. Magnitude 8. Caldera records. The letters are slightly misaligned, as if the archive printer was already failing when the copy was made. Beside the folder is a thin tray of volcanic ash sealed under glass. It looks harmless there, softer than dust, lighter than flour. A small label on the tray reads, "Not local." That is the clue that matters. A grain of ash found far from its source is a message that the atmosphere once carried the eruption farther than the landscape could remember. My office sits beneath the forward observation dome of my ship. Above the desk, the glass curves into darkness, and Earth hangs in the projection field as a quiet blue archive. No flames, no sound, only continents, oceans, cloud bands, and the slow rotation of a planet whose surface has been made and remade by heat escaping from within. I have opened many case files under that view. Some are written in starlight, some in bone. This one is written in collapsed ground and powdered glass. The central question sounds simple at first. What makes a volcano super? The answer is not the height of the volcano, or the violence of a single photograph, or the fear attached to a famous name. In careful scientific use, the term is tied to the scale of an eruption. More precisely, it is tied to a supereruption, an explosive, usually silicic event large enough to erupt more than 250 kilograms of material, or enough low-density tephra to cross the threshold commonly associated with the top of the volcanic explosivity index. The numbers need care. Volcanology has more than one way to measure size, and the differences matter. There is the bulk volume of loose or welded volcanic debris, which may include ash, pumice, and fragments spread across the surface. There is dense rock equivalent volume, the estimate of how much solid magma would have been required before vesicles, expansion, fragmentation, and deposition changed its form. There is erupted mass, which avoids some of the problems of comparing loose ash to welded ignimbrite. There is the Volcanic Explosivity Index, or VEI, a scale that uses volume and plume height, though at the very largest sizes, volume becomes the dominant measure. There is also eruption magnitude, written as a capital M based on mass. Those categories are not decorative bookkeeping. The Volcanic Explosivity Index was built to classify explosive eruptions across a wide range of sizes. At low and moderate values, plume height, volume, and descriptive eruption style can all help. At the top end, the scale becomes dominated by deposit volume, because no observer has stood beneath a VRC8 eruption with instruments and a clear sky. The largest events are reconstructed after the fact through what they left behind. A VEI8 threshold is commonly associated with more than 1,000 cubic kilometers of tephra, but tephra is not the same as magma. It is magma after expansion, fragmentation, transport, deposition, compaction, and sometimes welding. Dense rock equivalent is an attempt to reverse some of that transformation. If ash and pumice are full of holes, if a deposit is fluffy or loose, if pumice has vesicles where gas once expanded, then the deposit volume overstates the amount of original magma. Dense rock equivalent asks how much solid, unvesiculated magma would be needed to make the observed deposit. The conversion requires assumptions about density. It requires decisions about which deposits belong to the eruption. It requires estimates of what erosion removed and what later sediments concealed. The final number can look precise, but the route to that number passes through field judgment. Mass avoids some confusion because a kilogram remains a kilogram whether the deposit is welded or loose. Eruption magnitude, the capital M used in volcanology, is based on erupted mass. The threshold for a supereruption is often placed at M8, meaning erupted mass greater than 10 to the 15th kilograms. But mass must also be estimated through volume and density. The instrument is more consistent than volume alone, but it still depends on the geological record. On the screen in the archive vault, I sometimes place 3 cubes side by side. One cube is loose ash and pumice, low density and full of voids. One is welded tough, denser, compressed, and fused by retained heat. One is the dense rock equivalent, the imagined compact magma before eruption. They are related, but they do not occupy the same space. A listener may hear that a supereruption produces 1,000 cubic kilometers of material and picture a neat cube of magma underground. The rock record does not support that simplicity. The deposited material is a changed substance. There is also the problem of missing material. A very large explosive eruption can have an intra-caldera component, where material remains within the collapsed basin. It can have outflow ignimbrites, where pyroclastic currents spread across the surrounding region. It can have ashfall carried by high eruption columns and wind. In some eruptions, all 3 are preserved well enough to estimate. In many, they are not. The intra-caldera fill may be hidden beneath a lake or later lava. Ashfall may be scattered so thinly that it survives only in protected basins. outflow sheets may be deeply eroded or separated into remnants that no longer look connected. For ancient eruptions, the uncertainty grows. A deposit can be folded, faulted, altered, or buried. A caldera can be partly destroyed by later tectonics. The source may be unknown. Some of the largest known tuffs were recognized as volcanic long after they were first mapped as rocks. A giant eruption can outlive its volcano in the record, leaving a sheet of ashflow tuff without an obvious vent. In those cases, the deposit becomes a question as much as an answer. This is why catalogues of the largest eruptions are provisional. They are not simply lists of everything Earth has done. They are lists of everything geologists have found, identified, correlated, dated, and measured with enough confidence to include. The apparent frequency of supereruptions changes as old deposits are reinterpreted and new ones are found. A missing deposit is not evidence that no eruption occurred. A preserved deposit is not always evidence that the volume has been fully counted. Even so, the scale remains unmistakable. When an eruption crosses the M8 range, the uncertainty may be large, but the event is already beyond ordinary comparison. If the minimum estimate still requires hundreds of cubic kilometers of magma, the scientific problem is not whether the eruption was large. It is how large, how fast, through what vents, from what reservoir, and with what consequences. They decide whether an eruption sits near the boundary or far beyond it. A deposit of loose ash and pumice can occupy far more space than the dense magma that produced it. A welded pyroclastic flow deposit can be compact, heavy, and dense. A caldera may be eroded, buried, nested inside older collapsed structures, or partly filled by later lava. The deeper one reaches into the geological past, the less complete the scene becomes. So, when scientists speak carefully, they do not treat the word supervolcano as a magic label. A supervolcano is best understood as a volcanic system that has produced at least one supereruption. The system may later produce much smaller eruptions. It may spend tens of thousands of years in restless silence. It may emit lava flows, steam, gases, and earthquakes without coming close to repeating its largest act. The name belongs to a demonstrated capacity in the record, not to a permanent state of imminent eruption. That distinction is where the public story often goes wrong. The word itself has a strange history. It entered public awareness through documentaries, dramatizations, headlines, and the particular magnetism of Yellowstone. Scientists did not invent the popular version of the word in the clean way a committee might define a unit of measurement. They inherited it after it had already begun to move through public language. That made some volcanologists wary of it, and with reason. A word that carries too much fear can become less useful than the careful terms it tries to replace. But the word also points towards something real, the far end of explosive volcanism, where the scale of an eruption exceeds anything humans have directly watched. The scientific rescue of the term depends on tying it to evidence. A volcano should not be called super because it is famous, or restless, or large in a scenic sense. It should earn the label through the record of at least one immense silicic explosive eruption. Silicic matters because the physical behaviour is part of the category. These eruptions are usually driven by evolved magmas rich in silica, often rhyolite or dicite, with enough viscosity and volatile content to fragment violently. Explosive matters because a lava province that releases enormous basaltic flows over long intervals belongs to a different volcanic problem. Large igneous provinces can alter climate and life, and they deserve their own file, but their timescales, deposits, eruption styles, and gas release histories differ from short-lived caldera-forming supereruptions. This is why a supervolcano is less a shape than a demonstrated history. The volcano may look like a lake, a high plateau, a broken rim, a field of domes, or a place where steam escapes from wet ground. The event that made it super may be hundreds of thousands of years old. The system may have produced ordinary lava flows afterward. It may be monitored today because it is alive in a geological sense, while showing no sign that its largest behaviour is near. In ordinary speech, the label often clings to the site as if the site were always in its most extreme state. The science is more restrained. The label points backward first to what the rocks prove happened. There is a useful humility in that order. The case begins with the past, because the past is where the supereruption is known. Present monitoring may show unrest, heat, earthquakes, gas, or deformation, but present unrest does not automatically scale to the largest past event. The largest known eruption at a volcanic field sets the outer boundary of what that system has done, not a forecast of what it is doing now. The old files contain many rejected phrases: mega eruption, gigantic eruption, great eruption, cataclysmic eruption. Some are descriptive, some imprecise, some too theatrical. Supereruption survived because it gave the public a handle and then forced the scientific question: what exactly is the threshold? That threshold is not perfect, but it is usable when tied to erupted mass and explosive silicic behaviour. More than 10 to the 15th kilograms of erupted material is not an easy number to feel. It is easier to say that the eruption crosses into a range where deposits can cover regions, calderas can span tens of kilometres, and ash can become a marker in sediments far beyond the source. I keep a small notation in the margin of this file. The word is allowed only if the evidence is larger than the word. That is the rule that keeps the case from drifting into spectacle. A supervolcano is not a ticking clock. It is not necessarily overdue. It is not a giant cone waiting to explode on schedule. It is a geological system whose past includes an eruption so large that ordinary human experience gives us no direct comparison. The largest explosive eruptions known from the rock record are orders of magnitude larger than anything witnessed in recorded history. Mount St. Helens in 1980 was destructive and scientifically important. Pinatubo in 1991 affected global climate and gave modern instruments a powerful lesson in volcanic aerosols. Tambora in 1815 altered weather patterns and contributed to severe hardship across parts of the world. Yet the largest supereruptions dwarf them in erupted volume. The comparison is not a matter of drama, it is a matter of scale. In the archive vault, the old classification charts are stored in flat drawers, each sheet held beneath a pressure film to keep the brittle paper from curling. One drawer contains eruption volumes, another holds maps of ashfall thickness. Another lists caldera dimensions, dates, and deposit names. Younger Toba tuff, Huckleberry Ridge tuff, Lava Creek tuff, Oruanui, Bishop tuff, Fish Canyon tuff. The names are plain. They do not sound like events that could darken skies across continents. They sound like field sites. That is often how great violence enters the scientific record, as a measured layer, a mapped unit, a sample code, a date with uncertainty. The first human step toward understanding supereruptions was not to see one happen. It was to recognize their remains. Thick ash deposits around Lake Toba, vast sheets of ignimbrite in the American West, broad calderas at Yellowstone and Long Valley, the volcanic rocks of Taupo in New Zealand. The recognition came slowly because the deposits were too large to be understood at first as single events. A thin ash bed can be imagined as one eruption. A cliff hundreds of meters high, made from hot ash flows, asks for a larger explanation. A caldera tens of kilometers across asks for something larger still. A caldera is not merely a crater. A crater is often a surface wound around a vent. A caldera is a structural failure. The difference matters because it changes the scale of the forces involved. A large caldera records the response of the crust to withdrawal from below. The roof rock does not disappear in an explosion. Much of it subsides. It can drop as coherent blocks, fracture into pieces, tilt, founder, or collapse in stages. The eruption and the collapse are coupled, and in the larger systems that coupling can feed back on itself. At the beginning, magma reaches the surface through fractures or vents. Pressure drops near the conduit. Gas expands. Fragmentation sends ash and pumice upward. Material leaves the reservoir. If enough magma is withdrawn, the roof begins to lose support. The stress field changes. Ring fractures can propagate around the margin. Those fractures may become new pathways for magma, so the eruption migrates around the collapsing structure. Collapse can push magma outward like a piston, helping sustain discharge even as the reservoir pressure changes. This is the physical reason caldera-forming eruptions can be so large. They are not only eruptions through one pipe. They can become failures of an entire reservoir roof system. The ground participates. The crust, which had contained the magma, becomes part of the eruptive machinery once it starts to fail. There are several styles of collapse. Some calderas drop along relatively coherent ring faults. Some form by piecemeal subsidence, where blocks collapse irregularly. Some are trapdoor-like, hinged more on one side than the other. Some are nested, with later collapse inside older collapse. Some become resurgent when the floor is later pushed upward by magma, hot rock, or pressure beneath. In the field, these ideal categories can overlap. The final shape reflects magma withdrawal, roof strength, fault geometry, regional tectonics, and later modification. In the holographic evidence bay, the first model I showed was too clean. The archive's older teaching file drew a neat circular roof block dropping into a smooth chamber. It was useful, but misleading if taken literally. The next model is less elegant. The reservoir is not a sphere. Its upper boundary is uneven. The roof has inherited faults. The melt-rich zones are separated by crystal-rich material. Collapse begins along one segment, stalls, then jumps. An eruption column rises from one vent while a pyroclastic current escapes from another. The caldera does not form like a lid being removed from a jar. It forms like strong rock, reaching the end of its strength in several places at once. This also explains why caldera size cannot be converted into eruption volume by a simple formula. A broad caldera may collapse over a reservoir whose erupted volume is only partly preserved. A smaller caldera may have deep subsidence. Intracaldera fill may hide the amount of collapse. Resurgence may lift the floor. Erosion may remove rims. Later eruptions may bury faults. The relationship between caldera area and erupted volume is real in a broad sense, but the scatter is large enough to punish easy claims. The structure of the roof is especially important in the largest systems. A small magma chamber may erupt when internal overpressure fractures the surrounding rock. A very large reservoir can behave differently. As a reservoir grows wide, the roof must support itself across a greater span. If overpressure remains modest, eruption may be delayed, allowing the reservoir to grow. At some threshold, gravitational failure of the roof can become a central trigger. In that view, a supereruption may begin not because the reservoir has become a simple, overinflated balloon, but because the crust above it can no longer carry the load. There is no need to choose one mechanism for all cases. A real caldera eruption can involve overpressure, recharge, volatile exsolution, tectonic stress, roof foundering, and conduit opening. The important point is that the largest eruptions are mechanical events as much as magmatic ones. They happen at the boundary between molten material and brittle crust, where heat has weakened rock, pressure has accumulated, fractures have formed, and gravity is waiting. A crater is commonly excavated by explosion or impact at a vent. A caldera forms when the ground collapses after magma is withdrawn from below. In a large caldera-forming eruption, the magma chamber or melt-rich part of the reservoir loses support. The roof fractures along ring faults or complex collapse structures. Blocks of crust sink. The eruption may continue through vents around the collapsing margin. Pyroclastic currents move outward. Ash rises into high eruption columns and co-ignimbrite clouds. The landscape is changed both by what leaves the ground and by what falls back into the emptied space. The holographic evidence bay gives the process a shape. When I call up the Caldera model, the floor projection begins as a volcanic plateau seen from above. Lines of stress appear around a hidden reservoir. Then the model withdraws magma from beneath the surface, slowly at first, then in a rapid pulse. The roof bends, fractures link into a ring, the central block drops. Around it, hot material races outward in pale sheets. Above it, an ash column forms and spreads into the upper atmosphere. The animation is silent, which makes it more severe. There is no cinematic roar, only geometry changing under load. In the field, the evidence of such collapse is not always clean. Calderas can be altered by later eruptions. Lakes, glaciers, erosion, sediments, hydrothermal activity, and faulting. Yellowstone, for example, is not a single empty bowl with a neat rim. It is a volcanic field shaped by multiple large eruptions, later rhyolite flows, resurgent domes, tectonic structures, hydrothermal basins, and forested terrain. Long Valley is a caldera partly modified by later activity and regional tectonics. Toba is partly filled by a lake. Taupo's record is shaped by interactions between magma, water, wind, and the volcanic terrain of New Zealand. A supereruption leaves more than a hole. It leaves deposits that can be followed like testimony. Ashfall settles from the eruption column, sometimes hundreds or thousands of kilometers away. Ignimbrites form when pyroclastic density currents, mixtures of hot gas and volcanic fragments, sweep across the ground. If the deposit is hot and thick enough, the ash and pumice can weld together, becoming a dense volcanic rock. In some places, the rock preserves pumice flattened into streaks. In others, it forms cliffs, plateaus, or sheets draped over older topography. The word ignimbrite is useful because it keeps attention on the evidence rather than the spectacle. A pyroclastic density current is not simply ash blown sideways. It is a moving mixture of hot gas and volcanic particles, whose density, momentum, turbulence, temperature, and particle concentration change as it travels. Some currents are dilute and turbulent, capable of overtopping ridges. Others are dense near the ground, concentrated enough to scour, bury, and weld. A single large eruption can produce several kinds of currents at different times, from different vents, with changing composition and energy. When such a current stops, its deposit can preserve clues to the motion. A massive, poorly sorted layer may suggest rapid deposition from a dense flow. Crossbedding may record traction along the ground. Pumice size can decrease away from source. Lithic fragments, torn from older rocks in the conduit or caldera walls, may be concentrated near vents or at certain levels in the deposit. Welding records retained heat and load. Glass shards and pumice collapse into flattened textures as the deposit compacts. Devitrification can later convert volcanic glass into crystalline material, altering the rock while preserving parts of its original fabric. The deposits of supereruptions are often compound. What looks like one thick sheet may record multiple pulses. A flow unit can be emplaced, still hot, then covered by another. Cooling breaks can be subtle. Soil formation between units may indicate a long pause, while the absence of soil does not always prove that events were simultaneous. Paleomagnetic directions can help, because hot deposits cool through magnetic blocking temperatures and lock in the direction of Earth's magnetic field at that time. If several units share a distinctive direction, they may have cooled within a short interval. If directions differ, the units may be separated by enough time for the magnetic field to change. The full deposits tell a different part of the event. Ash and pumice carried upward in a Plinian column are sorted by wind, particle size, density, and plume height. Coarser pumice falls closer to source. Fine ash can travel far. Ash thickness can be mapped with isopachs, lines connecting equal deposit thickness, allowing reconstruction of dispersal. Grain size, componentry, and glass chemistry help identify whether ash in a lake core or archaeological layer belongs to a known eruption. In distant sites, the ash may be invisible to the eye, present only as cryptotephra recovered through laboratory processing. Cryptotephra is one of the most delicate forms of volcanic evidence. A layer may contain only a small concentration of glass shards dispersed in sediment. Under a microscope, with geochemical analysis, those shards can become a time marker. They can link a lake in Africa, a soil in India, or a marine core to a volcano thousands of kilometers away. For the Toba debate, this kind of evidence matters because it pins local environmental and archaeological records to the eruption horizon. Without the ash, the timing can blur. With the ash, the question becomes sharper. What changed immediately after this layer was deposited? In the evidence bay, I can enlarge a glass shard until it fills the wall. At that scale, it looks like a broken window fragment, curved at the edge where a bubble once stretched the melt. The shard began as magma, fragmented by expanding gas, carried through an eruption column, transported by wind, settled into sediment, survived burial, and waited until someone separated it from the mud. Its chemistry can match it to a source. Its position in the core can date an ecological change or the absence of one. A shard small enough to rest on a needle can connect a landscape to a volcano beyond the horizon. That is the true reach of a supereruption. The pyroclastic currents show the violence near the source. The ashfall shows the atmospheric reach. The caldera shows the structural collapse. The distal glass shows that the event entered records far from the volcano, where no one looking at the land would guess that Sumatra, Yellowstone, Taupo, or Long Valley had anything to do with the soil beneath their feet. An ignimbrite is a deposit made by a pyroclastic density current. The current itself can move at tremendous speed, but the deposit remains long after the motion ends. It is the cooled record of a ground-hugging cloud that was too hot to be weather, too dense to be ordinary air, and too mobile to be thought of as a simple avalanche. For a supereruption, the deposits can be vast. Some material remains inside the caldera as intra-caldera fill. Some spreads outward as outflow sheets. Some rises, spreads, and falls as ash across regions far from the source. Estimating the original volume requires all three, and often one or more are partly missing. The full deposit may be eroded, the intracaldera fill may be hidden, the outflow sheets may be buried by later volcanic activity. The farther back in time the eruption lies, the more the record has been edited by the planet itself. This is why the measurement of the largest eruptions is not as simple as drawing a line around a deposit on a map. Scientists measure thickness, grain size, density, distribution, chemistry, and stratigraphic position. They compare glass shards. They identify minerals. They estimate how much material was lost to erosion or hidden under younger rocks. They convert loose deposit volume into dense rock equivalent. They assign uncertainties, even when the public number appears clean. A number such as 1,000 cubic kilometers of erupted material should not be heard as an exact boundary carved into nature. It is a working threshold. It marks a scale beyond ordinary historical experience, a level at which an explosive eruption becomes capable of reshaping a region and disturbing the atmosphere. But it also sits inside the mess of field geology. Incomplete exposure, uncertain density, changing terminology, and the difficulty of reconstructing an event that no human instrument recorded. The archive has a separate shelf for Toba. Toba's shelf is not arranged like a simple disaster file. It begins with geology. Lake Toba occupies a huge caldera in northern Sumatra, roughly 100 kilometers long in the broad outline usually shown on maps. The Younger Toba Tuff is the youngest and largest of several major Toba eruptions, and it is the one that made the system central to discussions of supereruptions. Its deposits include extensive ignimbrites around the source and ash dispersed over a vast region. The eruption column and co-ignimbrite clouds carried fine material high into the atmosphere, and the ash became a stratigraphic marker across parts of Asia and beyond. The lake itself gives the case a deceptive calm. Water softens edges, forests return. Villages, roads, and fields grow around the caldera. A visitor sees weather, mountains, boats, and shoreline. The eruption is present as shape rather than spectacle. The caldera is the absence filled with water. The geological reconstruction of Toba has always required large corrections. Some erupted material remains in and around the caldera. Some was carried outward as pyroclastic flows. Some spread as ash. Some lies beneath water or vegetation. Some has been eroded or reworked. Estimates of the total dense rock equivalent volume have changed as methods and assumptions changed. That variation should not be treated as failure. It is the normal cost of reconstructing a prehistoric event at continental scale. Toba also helps clarify why eruption size and climate impact cannot be equated too directly. The volume of magma tells one part of the story. The sulfur content and release tell another. The height of injection matters. The season matters. The latitude matters. The chemistry of the magma matters. But sulfur release is not always proportional to erupted volume in a simple way. A huge eruption with one sulfur budget and injection pattern can have a different climate effect from a smaller eruption that efficiently injects sulfur into the stratosphere. The early catastrophe hypothesis connected Toba to a severe volcanic winter and a possible bottleneck in human evolution. It was a compelling idea because the timing seemed suggestive, and the eruption was large enough to feel capable of global consequences. But compelling is not the same as demonstrated. The hypothesis had to pass through the sediment record, the archaeological record, genetic evidence, and climate physics. Across those domains, the result became less simple. In India and parts of Africa, the search for Toba ash and cryptotephra allowed scientists to align archaeological layers with the eruption. In some records, human activity appears to continue across the Toba horizon. At Lake Malawi, high-resolution records did not show the dramatic cooling or ecological collapse that a strong universal volcanic winter might predict for that region. Those findings did not erase Toba's climate effect. They changed the question. Instead of asking whether Toba devastated the whole world in the same way, researchers asked where the effects were severe, where they were muted, and why. That shift is important for the eventual narration. It prevents the human evolution section from becoming a myth of a single, near-extinction moment. The more rigorous version is more interesting. A vast eruption occurred. It dispersed ash across major parts of the old world. It injected sulfur into the atmosphere with uncertain magnitude. Climate models suggest significant cooling and hydrological changes, but the response was geographically uneven. Some regions that mattered for human populations may have acted as relative climate shelters. Archaeological continuity in some areas can coexist with severe impacts elsewhere. The Toba file is therefore a lesson in resisting one-map thinking. A global mean temperature curve is useful, but no human group lived in the global mean. People lived in seasonal rainfall, local plant communities, river valleys, coasts, forests, savannas, and monsoon systems. A climate anomaly that is devastating in one region may be survivable or barely detectable in another. The human story, if it is included, should be anchored there, in uneven exposure, resilience, and the limits of the evidence. The folder is thick, and not because the case is settled. Toba is useful because it is large, relatively recent in geological terms, and tied to debates that reach beyond volcanology into climate, ecology, and human evolution. The younger Toba tuff erupted about 74,000 years ago from Sumatra. It expelled an immense volume of magma, generated ash that travelled across great distances, and left deposits that became time markers in sediments and archaeological sites. But Toba also became a cautionary example of how a dramatic idea can outrun the evidence. For years, it has been linked in public accounts to a severe volcanic winter and a near extinction of modern humans. The underlying question is legitimate. A tropical supereruption can inject sulfur into the stratosphere. Sulfate aerosols can reflect sunlight and cool the surface. cooling can affect rainfall, growing seasons, ecosystems, and human groups. Yet the size and distribution of those effects depend on details that are difficult to know for a prehistoric eruption: sulfur release, injection altitude, season, background climate, aerosol microphysics, ocean response, and atmospheric circulation. The climate file is therefore not a single verdict. It is a comparison between models and records. Lake sediments, pollen, phytoliths, charcoal, archaeological continuity, ice core signals where available and interpretable. Tephra layers that tie a site to the eruption horizon. Climate simulations that test plausible sulfur emissions and aerosol behavior. No one line of evidence is enough by itself. The instrument room is one deck below the archive. The displays in that room are arranged as layered time. The first layer is the eruption itself: sulfur dioxide rising from vent columns and co-ignimbrite clouds into the stratosphere. The second layer is chemistry: sulfur dioxide oxidizing into sulfuric acid vapor, then nucleating and condensing into sulfate aerosols. The third layer is microphysics: particles growing, colliding, coagulating, settling, and changing their size distribution. The fourth layer is radiation: incoming shortwave sunlight reflected back to space, outgoing longwave radiation partly absorbed and re-emitted, clouds responding, surface fluxes shifting. The fifth layer is climate: temperature, precipitation, circulation, monsoon strength, ocean heat uptake, and recovery. Older mental pictures often stopped too early in that chain. They treated more sulfur as almost directly equivalent to stronger and longer cooling. The newer models force a correction. When sulfur loading becomes extremely large, the aerosol particles do not simply remain small and efficient. They can grow large enough that their optical behavior changes. Larger particles scatter sunlight differently and fall out faster. The radiative forcing becomes self-limited in ways that matter for supereruption scale injections. That is why aerosol size is not a technical footnote. It changes the whole climate story. If particles remain small, the aerosol veil can be optically efficient and persistent. If particles grow, the same sulfur mass can produce a weaker or shorter-lived cooling than expected. The atmosphere becomes less like a passive container and more like a reacting system whose internal physics determines the outcome. The models also show the importance of latitude and season. A tropical eruption can distribute aerosols into both hemispheres, but stratospheric circulation changes with the time of year. The Brewer-Dobson circulation, seasonal shifts, and hemispheric transport patterns can steer the aerosol burden unevenly. If forcing is stronger in one hemisphere, the intertropical convergence zone can shift. Monsoons can weaken or move. Rainfall changes can matter as much as temperature changes for ecosystems and people. In a chemistry climate model, those processes must be represented by equations and approximations. The model grid has finite resolution. Aerosols are placed into size bins. Chemical reaction rates are specified. Ocean and sea ice components exchange energy with the atmosphere. The simulation is run many times because a single run may be influenced by the initial state of the climate system. One ensemble member may begin with one phase of ocean variability, another may begin with a different one. This is not indecision. It is how a chaotic climate system is sampled. A useful model result is therefore not only a line that says the planet cooled by a certain number of degrees. It is a distribution of possible responses. It can say that a given threshold of cooling is very likely in one region and unlikely in another under a particular sulfur scenario. It can show that precipitation changes are not always strongest, where temperature changes are strongest. It can show that the ocean continues to carry the memory of the forcing after aerosols decline. The Toba simulations that matter most for this episode do not give a single apocalyptic answer. They show strong global and regional effects for plausible sulfur emissions, with the largest responses often concentrated over northern continental interiors in high sulfur cases. They also show muted cooling probabilities over much of Africa in scenarios where older narratives might have expected severe disruption. They allow the climate and archaeological evidence to occupy the same case file without forcing one to erase the other. The phrase volcanic winter should therefore be used sparingly. It can describe a broad idea: surface cooling caused by stratospheric volcanic aerosols after a very large eruption. But it can also smuggle in an image of uniform darkness, universal crop failure, and decade-long collapse. The science is more conditional. A better passage should speak of sulfate aerosols, radiative forcing, regional cooling, hydrological disruption, aerosol growth, and uncertainty. The language may be less dramatic, but it carries more truth. I leave the instrument room with the map still running behind me, because the room is good at refusing conclusions that are too smooth. Every screen shows a different variable. One shows aerosol optical depth. One shows precipitation anomaly. One shows surface temperature. One shows particle effective radius. None of them is the eruption. Each is one trace of the eruption moving through a different part of the Earth system. It is narrow, with cabinets on both walls and old status lights that never fully go dark. When I route the Toba climate models through the display wall, the ship fills with maps of temperature anomaly and precipitation change. The maps do not show a single uniform winter. They show patchwork, stronger cooling in some northern continental interiors, more muted responses in parts of Africa and the southern hemisphere, changes in rainfall that do not simply mirror changes in temperature, a planet responding through atmosphere, ocean, ice, land, and season. This is one of the most important lessons of the Toba case. A supereruption can be globally significant without having the same effect everywhere. In some model ensembles, high sulfur emissions produce severe cooling over parts of Asia, Europe, and North America, while much of Africa shows a lower probability of extreme annual cooling. That pattern helps explain why some paleoclimate and archaeological records do not show the kind of universal collapse once proposed. It does not make Toba harmless. It makes Toba more complicated and more scientifically interesting. The atmosphere is not a passive screen. When sulfur dioxide reaches the stratosphere, it oxidizes and forms sulfate aerosols. These particles scatter incoming sunlight. After modern eruptions such as Pinatubo, the effect is measurable: a temporary reduction in global temperatures, changes in radiation, and altered atmospheric chemistry. For a much larger eruption, one might expect a simple scaling: more sulfur, more aerosols, more cooling. But aerosol physics resists that simplicity. At very high sulfur loads, particles can grow larger through condensation and coagulation. Larger particles are less efficient at scattering sunlight per unit mass and can fall out more quickly. The same added sulfur that increases the aerosol burden can also change the particle size distribution in a way that limits the climate response. This is why some modern climate simulations of Toba-scale eruptions produce cooling that is severe but shorter and weaker than older estimates that assumed smaller Pinatubo-like particles at enormous scale. That caveat matters for the tone of the entire episode. A supereruption is not a myth. It is not a harmless curiosity. But neither should it be flattened into a single phrase like volcanic winter without specifying what model, what sulfur amount, what region, what season, what proxy record, and what uncertainty. Science does not become weaker when it refuses a simple catastrophe story. It becomes more useful. There is another reason the word supervolcano can mislead. It can make these systems sound like they exist for one purpose: to produce the largest possible eruption. The rock record shows a different pattern. Systems capable of supereruptions often produce many smaller events. They can erupt lava flows after the great caldera forming eruption. They can have hydrothermal explosions, small rhyolite domes, basaltic vents near the system, or long stretches of deformation and seismicity without eruption. Yellowstone is the familiar example, so it must be handled with particular care. Its familiarity is useful only if it is disciplined. Yellowstone is not the only supervolcano, and it is not the best stand-in for every caldera system on Earth, but it is unusually well studied, and its public visibility makes it a good place to correct several misconceptions at once. The Yellowstone volcanic field sits above the track of a mantle hotspot interacting with North American crust. Over millions of years, that hotspot track left a chain of volcanic centers along the Snake River Plain before reaching the present Yellowstone region. The large caldera-forming eruptions are only part of that history. The system also produced many rhyolitic lava flows and smaller eruptions, and it remains one of the most energetic hydrothermal systems on the planet. The three major Pleistocene caldera-forming eruptions are usually named through their deposits. The Huckleberry Ridge Tuff, around 2.1 million years old, is the largest of the Yellowstone events and one of the largest known explosive eruptions of the Quaternary. The Mesa Falls Tuff followed around 1.3 million years ago. The Lava Creek Tuff, around 631,000 years ago, formed the present Yellowstone caldera. Those names matter because they remind us that the eruption is known through rock units, not through an eyewitness account. After the Lava Creek event, Yellowstone did not become inert. Rhyolite lava flows continued, some very large by ordinary volcanic standards, and the youngest of those are tens of thousands of years old. Heat still moves through the system. Water still circulates through fractured rock. Geysers and hot springs release heat and gases. Earthquakes occur by the thousands in many years. The ground rises and falls over decades. None of that should be dismissed. None of it should be inflated into a forecast of catastrophe. The geophysical picture beneath Yellowstone is a picture of heat, partial melt, mush, fluids, and structure. Seismic waves slow in hot or partially molten zones. Some studies have inferred large volumes of crystal melt mush in the shallow to mid-crust, but the estimated melt fraction is generally far below what would be required for a single large eruptible body. A mush with 10 or 15% melt can be thermally and geophysically important without being ready to erupt. Melt must be extracted, concentrated, and connected before it becomes mobile at the scale needed for eruption. This is a subtle point, and it is worth taking time with in the script. A headline may say there is a huge magma body beneath Yellowstone. A careful narration should ask what kind of body. How much is melt? How much is crystal? Is it connected? Is it eruptible? At what depth? With what uncertainty? Geophysical imaging sees contrasts in wave speed, density, conductivity, or deformation, not a labelled reservoir. Interpretation is required. The hydrothermal system complicates everything. Yellowstone's surface heat flow is enormous, and much of it is carried by hot water and steam. Snow and rain recharge aquifers in volcanic rocks. Water descends, heats, reacts chemically, dissolves gases and minerals, then rises through fractures. Hydrothermal fluids can alter rocks, seal pathways, open new ones, trigger small explosions, and influence gas measurements. They can also contribute to ground deformation and seismicity. In a caldera, water is not background scenery. It is part of the machine. There have been large earthquake swarms at Yellowstone, including the notable 1985 swarm. There have been episodes of uplift and subsidence measured by levelling, GPS, and satellite radar. Some areas of the caldera have risen while others subsided. Lake terraces suggest longer histories of vertical motion. These changes are real, but their causes can be mixed. Tectonic stress, hydrothermal fluids, gas movement, and magma intrusion may all contribute. The difficulty is not lack of data alone. It is that several processes can make overlapping signals. That is the reason modern monitoring depends on networks, not isolated signs. A single earthquake swarm means less than a swarm combined with sustained deformation, gas changes, thermal anomalies, tremor, and petrological evidence from erupted material if an eruption begins. Forecasting requires pattern recognition across instruments informed by the baseline behaviour of the system. To know what is abnormal, scientists first have to know the full range of normal unrest. Yellowstone's greatest value in this episode is therefore not fear. It is method. It lets the listener see how a famous supervolcano is studied as a living system, through maps, seismometers, satellites, gas sampling, thermal measurements, geochemistry, and historical comparison. The more carefully we study it, the less useful the simple panic story becomes. Its name attracts attention, and attention often distorts risk. The Yellowstone Plateau volcanic field has produced multiple very large caldera-forming eruptions in the past, including the Huckleberry Ridge Tuff around 2.1 million years ago, the Mesa Falls Tuff around 1.3 million years ago, and the Lava Creek Tuff around 631,000 years ago. It has also produced many later lava flows, including rhyolitic flows far younger than the last supereruption. It remains a volcanic and hydrothermal system. It has earthquakes, ground deformation, heat flow, gases, geysers, hot springs, and a complex subsurface. Those facts do not mean that Yellowstone is on the edge of a supereruption. They mean it is active enough to monitor and important enough to study. The difference is essential. At calderas, unrest can come from magma, hydrothermal fluids, tectonic stress, gas movement, or interactions among all of them. Earthquake swarms can occur without eruption. Uplift can reverse into subsidence. Gas flux can be influenced by the hydrothermal system. The surface may move because fluids shift pressure at depth. A restless caldera is not the same as a ready eruption. In the ship's long corridor outside the research bay, the hull sometimes gives a faint metal tick as it adjusts to thermal gradients. The first time I heard it, many years ago by the ship's internal clock, I traced the sound through 3 decks before I understood it. Expansion, contraction, stress moving through structure, a signal yes, but not an alarm. Volcano monitoring often begins with the same discipline. Listen carefully, then resist the first dramatic interpretation. At Yellowstone, monitoring includes seismic networks that record earthquakes, GPS stations that detect ground motion, INSAR measurements from satellites that map deformation, gas measurements, thermal observations, geological mapping, and studies of hydrothermal features. Seismic tomography images zones where waves travel more slowly, sometimes consistent with partial melt or hot rock. Gravity measurements constrain density contrasts. Heat flow and gas emissions show that the system releases large amounts of energy and carbon dioxide. Each method sees a different property. None sees the whole system alone. This is why the modern image of a magma reservoir is not a bright red lake under the park. Beneath large silicic volcanic systems, magma may exist as crystal-rich mush, melt lenses, sills, dikes, partially molten zones, and hotter basaltic inputs deeper in the crust. The eruptible portion, the part with enough melt and mobility to erupt, may be much smaller than the total warm reservoir. A geophysical anomaly can indicate heat and partial melt without indicating a large body of eruptible magma. The specimen archive holds the more intimate part of the Yellowstone case. A zircon crystal is a small object with an unusual talent for survival. It incorporates uranium when it crystallizes, but it tends to reject lead. Over time, uranium isotopes decay into lead isotopes at known rates. Measuring those isotopes can give an age for the growth of the crystal or part of the crystal. In volcanic systems, where timing is central, zircon becomes more than a mineral. It becomes a clock that can be carried through eruption and preserved in the deposit. The clock is not always simple. A zircon can have a core older than its rim. It can be inherited from older crust, recycled from earlier magma, or grown in several stages inside a reservoir that changed through time. That complexity is the reason scientists use imaging, spot analyses, and careful selection. A polished grain under cathodoluminescence can show internal zoning, cores, rims, growth bands, resorbed boundaries. Each zone may have its own age and chemistry. For Yellowstone, paired measurements are powerful. Uranium-lead dates constrain when zircon crystallized. Oxygen isotopes can indicate whether magma interacted with hydrothermally altered rocks near the surface or with deeper crustal sources. Hafnium isotopes can distinguish juvenile mantle-derived contributions from older crustal material. Trace elements such as europium anomalies can record feldspar crystallization and the evolving chemistry of the melt. When the same crystal carries several kinds of data, the reservoir begins to look less like a volume and more like a history. The Yellowstone zircon studies show isotopic diversity among crystals that are close in age. That means multiple magma batches with different sources or histories coexisted close to eruption. Some batches carried more juvenile mantle-like signatures, some showed stronger crustal influence, some recorded interaction with rocks previously altered by hydrothermal fluids. The reservoir was not a perfectly stirred tank. It contained sub-reservoirs, batches, and heterogeneity that remained preserved until eruption. The preservation of oxygen isotope differences is especially useful. At high temperature, diffusion works to erase sharp isotopic contrasts over time. If zoning survives, the crystals cannot have sat for too long under conditions that would have homogenized them. That gives an independent check on storage times. In the Yellowstone work, the data support rapid assembly of large eruptible reservoirs over thousands to tens of thousands of years, rather than a single body of eruptible liquid stored unchanged for hundreds of thousands of years. This does not mean the entire magmatic system was young. Heat and magma input may have affected the crust for much longer. Earlier intrusions, older mush, and hydrothermal alteration created the materials later remobilized. The distinction is between the long preparation of a volcanic province and the shorter assembly of the eruptible magma that feeds a specific supereruption. The deep system can be old, while the final eruptible arrangement is comparatively young. In the specimen archive, that distinction feels almost physical. The older rocks are the shelves, the long-built structure. The zircon rims are the fresh labels, written shortly before the drawer was opened. The eruption carries both into the deposit: old inheritance and recent assembly, crustal memory and pre-eruptive change. This kind of evidence also changes what monitoring can promise. If large eruptible reservoirs assemble on timescales of hundreds to thousands or tens of thousands of years, then detecting them depends on when in that process the system is observed and what instruments can resolve. A broad region of mush may be visible geophysically long before it is eruptible. A melt-rich body may be smaller than the resolution of an imaging method. The final concentration of eruptible magma could be difficult to see until the system has already changed substantially. That does not make monitoring futile. It makes monitoring more important. If the transition from warm mush to eruptible reservoir is the critical step, then repeated measurements through time are essential. A single image is a still frame. A network provides motion. Zircons tell us how past reservoirs assembled. Instruments watch whether present systems are reorganizing. The two forms of evidence meet across time, one in crystals, one in signals. In one drawer are thin sections and sample records. In another, zircon age tables. Zircon crystals are small, durable, and chemically informative. They can survive inside magma, recording growth zones that preserve uranium lead ages and isotopic compositions. When scientists analyze zircons from Yellowstone's great tuffs, they are reading a set of mineral clocks and chemical diaries. Those crystals show that the magma systems feeding Yellowstone's supereruptions were not necessarily stored as one simple, long-lived vat of liquid rhyolite. High-precision UPB dating and isotope measurements suggest rapid assembly of multiple magma reservoirs or batches before eruption, in some cases over thousands to tens of thousands of years. Oxygen and hafnium isotopes point to complex sources involving mantle-derived melt, old crust, and hydrothermally altered shallow rocks. The picture is dynamic. Repeated injections, remelting, mixing, crystallization, and assembly of eruptible magma from a larger transcrustal system. The timescale is striking. A caldera forming eruption may be prepared by processes that operate for a long time at depth, while the final assembly of eruptible magma can be comparatively short in geological terms. That does not mean a supereruption appears without warning. It means the presence of a broad hot system is not enough. The system must gather a sufficient volume of eruptible magma, retain gas, overcome mechanical limits, and connect to the surface. This is where the idea of crystal mush becomes useful. A mush is a mixture of crystals and melt, in which the crystal fraction is high enough to resist free flow. Interstitial melt can sometimes be extracted from such mush zones, especially when the system is heated, recharged, or reorganized. The extracted melt may be silica-rich, viscous, and volatile-bearing, the kind of magma that can produce explosive eruptions if enough of it accumulates and begins to ascend. Rhyolite is central to many supereruptions because of its physical properties. It is rich in silica, and that makes it viscous. A viscous magma resists flow and can trap gas bubbles. If dissolved water and other volatiles exsolve as pressure drops, bubbles grow. If the bubbles cannot escape, pressure builds. Fragmentation can follow, turning magma into ash, pumice, crystals, and gas. A basaltic lava can flow freely in many settings, but rhyolitic magma can behave like a sealed, gas-rich system under stress. That does not mean all large volcanic events are the same. Flood basalts and large igneous provinces can erupt enormous volumes of lava, and they have their own connections to climate and mass extinction, but they are not the same as explosive silicic supereruptions. A flood basalt province may release huge volumes over many eruptions across long intervals. A supereruption, in the sense used here, is a short-lived explosive event from a volcanic system capable of ejecting immense quantities of fragmental material. Mixing the two categories blurs important differences in timescale, eruption style, deposits, gases, and hazards. The hydroponics bay is the last place one might expect to think about magma. Yet the bay is useful because it makes the problem of extraction visible. Nutrient solution moves through a porous tangle of roots. Most of the bay is not open water. Flow depends on pathways. If a filter clogs, pressure changes. If a channel opens, fluid concentrates there. The system's behaviour depends on how connected the liquid is. A crystal mush has a related problem, though under vastly different conditions. When crystals occupy much of the volume, melt remains between them, but it may not move freely. At some crystal fractions, the mush can behave like a rigid framework with liquid in the pore spaces. Melt extraction then depends on compaction, buoyancy, deformation, gas-driven segregation, reheating, and the formation of channels or lenses. The melt that escapes can be more evolved than the mush it came from, enriched in silica and volatiles. This helps explain the relationship between plutonic and volcanic rocks. Many large bodies of granitic rock exposed at the surface today may be the solidified remains of ancient magma reservoirs or mush zones. Their volcanic counterparts are the erupted portions, melt-rich caps, lenses, or extracted liquids that reached the surface. The plutonic record and the volcanic record are not separate worlds. They are different exposures of the same crustal magmatic processes, one frozen underground, one expelled. In some tectonic settings, mantle magma forms by decompression, rising because pressure decreases as mantle material ascends. In others, such as subduction zones, water and other volatiles from the slab lower melting temperatures in the mantle wedge. Those different origins influence the magmas that eventually feed crustal reservoirs. Hotter, drier, more reduced systems can produce one kind of rhyolite lineage. Colder, wetter, more oxidized arc systems can produce another. The trace elements and mineral assemblages differ because water content, oxygen fugacity, pressure, and temperature determine which minerals crystallize and which elements remain in the melt. The terms hot-dry and cold-wet are not mood. They describe physical and chemical paths. A wet magma may saturate in volatiles at a less evolved composition, making intermediate eruptions more likely. A drier system may delay volatile saturation until the melt has evolved further, contributing to bimodal volcanic fields where basalt and rhyolite dominate, while intermediate lavas are less common. That pattern is part of why some hotspot and rift-related systems can build large volumes of rhyolitic magma. Water plays a double role. Dissolved water lowers melt viscosity and affects crystallization. But when pressure drops and water exsolves as vapor, bubbles grow. In a viscous rhyolite, bubbles can remain trapped long enough to fragment the magma violently. The same volatile that helped make the magma mobile at depth can help destroy it during ascent. Temperature is just as important. A system that is too cold may be locked in crystal-rich mush. A system heated by new mafic intrusions can rejuvenate. Crystals may partially dissolve. Melt fraction can increase. Volatiles may be added or redistributed. The reservoir can shift from stored to mobilized. But reheating alone is not enough. The melt must gather, remain connected, and find a path to the surface. The ship's hydroponics bay has sensors for flow rate, nutrient chemistry, temperature, and pressure. If I had only one sensor, I could misunderstand the whole system. Magmatic systems are the same. Petrology gives one set of constraints. Geophysics gives another. Gas chemistry gives another. Deformation gives another. A supereruption requires the alignment of many conditions, and no single instrument or mineral records all of them. Rows of plants grow under measured light, their roots suspended in nutrient channels. The system works because flow is slow, pressure is controlled, and every valve has a tolerance. When a pump shifts rate, the whole loop responds. A magmatic system is not built with valves or intentions, but it also depends on flow paths, pressure, volatile content, temperature, and permeability. A reservoir may store heat for a long time, and then reorganize when new magma enters, when crystals settle or melt, when gas accumulates, or when the surrounding crust begins to fail. The triggering of a supereruption remains one of the difficult questions. Smaller explosive eruptions can be triggered by magma recharge, volatile saturation, overpressure, earthquakes, or structural failure. For very large caldera systems, internal overpressure alone may not be sufficient, or may not develop in the same way. Some models suggest that as reservoirs become very large, the strength and stability of the roof, gravitational stresses, and the geometry of the system become central. Collapse may begin when the roof can no longer be supported, and once collapse starts, it can help sustain the eruption by forcing magma outward. A useful way to phrase the problem is this: why does a large silicic reservoir fail when it does? And why did it not fail earlier? If a system erupts too often, it may relieve pressure and never accumulate the volume needed for a supereruption. If it stores magma too cold or too crystalline, it may not have enough mobile melt. If it receives heat and new magma but remains sealed, it may grow toward a threshold. The final event may depend on the balance between magma supply, crustal strength, volatile behavior, reservoir shape, and tectonic stress. There is no single master key. The Bishop Tuff at Long Valley, the Oruanui eruption at Taupo, the younger Toba tuff, the Yellowstone tuffs, and older ignimbrites in places like the San Juan volcanic field did not all occur in identical settings. Some are related to subduction zone arcs, some to hotspots or extension. Some are wetter, some hotter and drier, some more influenced by crustal recycling. The common theme is not a single recipe, but a set of conditions that allow large volumes of silicic, explosive magma to accumulate and erupt. The cartography table displays these systems as points and outlines across Earth. I begin with Taupo because it changes the emotional register of the file. The Oruanui eruption in the Taupo volcanic zone of New Zealand is often cited as the youngest well-documented supereruption, occurring about 26,500 years ago. It was enormous, but it also had a particular complexity. Interaction with water, multiple phases, widespread fall deposits, pyroclastic flows, and changes in eruption style through time. It reminds us that a supereruption is not necessarily one steady blast. It can be an evolving sequence, with vents, water, magma, and atmosphere changing their roles as the eruption proceeds. Taupo also shows why a volcanic system can produce a supereruption and later produce much smaller but still significant eruptions. The Taupo eruption around 1,800 years ago was not a supereruption, but it was one of the most powerful eruptions of the late Holocene. In a human sense, it would be a major catastrophe. In the classification of supereruptions, it is much smaller. That contrast is useful. It helps keep scale honest. A supervolcano does not need to repeat its maximum behavior to be hazardous. Long Valley offers another kind of lesson. The Bishop Tuff, erupted around 760,000 years ago, is one of the classic studied ignimbrites. Its deposits have been used for decades to understand zoned magma chambers, eruption dynamics, and caldera collapse. The Long Valley caldera has also shown modern unrest, including uplift and earthquake activity, without a magmatic eruption. It therefore belongs beside Yellowstone in the monitoring section, a place where the past proves capacity, while the present teaches caution in interpreting unrest. The Bishop Tuff is valuable because it preserves evidence of a chemically and thermally structured magma body. Early erupted material can differ from later erupted material. Crystals and glass record gradients in temperature, composition, and volatile content. A large eruption can tap the reservoir in an order, sampling the upper parts first and deeper or different portions later. The deposit is not only the result of eruption, it is a cross-section through the reservoir's pre-eruption organization, scrambled into stratigraphy. Then there is Fish Canyon Tuff, from the San Juan volcanic field in Colorado, among the largest known explosive eruptions in the record. It is older than the Quaternary examples and belongs to a great volcanic flare-up. Its size pushes the category beyond the already extreme. For an episode like this, Fish Canyon does not need a long case study, but it deserves a place in the scale section. It shows that the largest known events are not all recent, not all famous to the public, and not all tied to modern monitoring anxieties. Ira, Kikai, Aso, and other Japanese caldera systems add another correction. Several active supervolcanoes are in arcs where subduction supplies the magmatic engine. Some have produced huge eruptions in the late Quaternary or Holocene and continue to host active volcanic behavior. This matters because the public sometimes treats Yellowstone as if it defines the category. It does not. Supervolcanoes occur in different tectonic settings, with different magma chemistries, different hazards, and different monitoring challenges. The map also includes Valles Caldera in New Mexico, a system whose older supereruptions and younger activity show how caldera complexes can persist through multiple eruptive cycles. Atitlan in Guatemala belongs to the same broader lesson. The geography of supervolcanoes is global, shaped by subduction zones, rifts, hotspots, and crustal conditions. The distribution is not random, but it is wider than the common thumbnail image of one American park. On the cartography table, I keep the active systems in one layer and the ancient large tuffs in another. The active layer asks how we monitor and prepare. The ancient layer asks how Earth behaves at the far end of volcanic productivity. They overlap, but they are not the same. A system can be active and not close to a large eruption. A giant tuff can preserve an eruption from a volcanic system that has long since gone quiet or been dismantled by erosion. There is a temptation to rank these systems as if the largest number alone carries the most meaning. But size is only one axis. Recency, preservation, proximity to populations, monitoring coverage, magma composition, sulfur budget, water interaction, and tectonic setting all shape the scientific and human significance. A smaller caldera-forming eruption in the wrong place at the wrong time could be more damaging to society than a larger ancient eruption in an unpopulated region. The science of supervolcanoes is therefore not a scoreboard. It is an attempt to understand how extremes form, how they are recorded, and how they might be recognized before they occur. Sumatra, Wyoming, New Zealand, California, Japan, Guatemala, New Mexico. The map is not evenly filled. Supervolcanoes require particular tectonic and magmatic circumstances. Thick continental crust or mature arc crust can help stall basaltic magma, allowing heat transfer, differentiation, crustal melting, and long-lived reservoirs. Regions with high magma flux can precondition the crust. Some systems repeat, others may be first-time events. That last point prevents another oversimplification. A known supervolcano is known because it has already produced a supereruption. But not every future supereruption must come from a place already famous for one. Geological records show that large silicic systems can develop in volcanic provinces where the necessary conditions come together. The absence of a famous label is not the same as the absence of risk. At the same time, the rarity of the events means that annual probability remains low from a human perspective. Risk is a difficult word in this file. The near-field hazard is the most immediate. Pyroclastic density currents from a large caldera-forming eruption could move across vast areas near the source, destroying nearly everything in their path. These currents are hot, fast, particle-rich, and dense enough to bury landscapes. Survival within their main path would not be a matter of sheltering in place. It would depend on being outside the affected zone before the event. Ashfall creates a different kind of hazard because it spreads farther and lasts longer. A few millimeters can disrupt daily life. Centimeters can damage crops, contaminate water supplies, clog machinery, and create respiratory hazards. Thicker accumulations can collapse roofs, especially when ash becomes wet. Ash is abrasive. It can damage engines, power systems, electronics, pumps, vehicles, and aircraft. It can turn roads slick, reduce visibility, and require removal on a scale that overwhelms ordinary infrastructure. Aviation is especially vulnerable because volcanic ash is not smoke. It is pulverized rock and glass. In jet engines, ash can melt and adhere to turbine components, causing serious damage or failure. A super-eruption-sized ash cloud would challenge airspace management over immense regions. Even much smaller eruptions have caused major aviation disruptions. At supereruption scale, the issue would no longer be local rerouting around a plume. It could become a continental or hemispheric logistics problem. Agriculture would face several kinds of stress. Ash can physically cover leaves and soil, abrade plants, reduce photosynthesis, and alter water infiltration. Livestock can be affected by contaminated feed and water. Fluorine and other elements in ash can create poisoning hazards in some eruptions. Climate forcing could shorten growing seasons or shift rainfall. A society with stored grain, global trade, mechanized agriculture, and satellite forecasting has advantages ancient populations did not, but it also has dependencies that can fail in chains. Power systems, water treatment, communications, and transportation would all face ash-related stress. Wet ash conducts electricity better than dry ash and can flash over insulators. Water systems must handle turbidity and chemical changes. Roads and rail lines require clearing. Drainage systems clog. Buildings not designed for ash load become vulnerable. Cleanup creates its own problem. Where to move the ash, how to keep it from being remobilized by wind, how to protect workers, how to restore machinery. The climate hazard is slower and broader. Sulfate aerosols could reduce sunlight, cool surfaces, shift rainfall, and alter atmospheric circulation. The exact pattern would depend on the eruption, but the consequences could be felt through food systems, water resources, ecosystems, and public health. The most serious social effects might come not from darkness in a dramatic sense, but from multiple years of agricultural stress across regions that already operate near margins. Risk planning for such events is difficult because frequency is low. Humans tend to prepare for events that have happened recently or repeatedly within institutional memory. Supereruptions fall outside that memory. The most recent well-documented one occurred long before writing. Cities, electrical grids, aviation, industrial agriculture, and global supply chains. The absence of historical experience makes imagination necessary, but imagination must be constrained by evidence. This is another place where the episode should remain calm. Preparedness is not panic. It is the ordinary extension of scientific knowledge into planning, monitoring networks, ashfall models, communication systems, aviation protocols, food reserves, infrastructure design, and international coordination are all more useful than apocalyptic speculation. The goal is not to make the listener afraid of a famous caldera. The goal is to show how a rare hazard becomes legible. The hazard from a supereruption would be profound. Near the source, pyroclastic density currents could devastate enormous areas. Ashfall could collapse roofs, contaminate water, damage machinery, reduce visibility, disrupt aviation, and harm agriculture. Fine ash is abrasive and persistent. Sulfur aerosols could alter climate for years, changing temperature and precipitation patterns. Modern global systems, with long supply chains and dense populations, would be vulnerable in ways ancient ecosystems were not. But risk is not only severity, it is severity combined with likelihood, exposure, preparedness, and uncertainty. A supereruption is a high-consequence, low-frequency event. That places it in a difficult category for public communication. Too much drama produces fatalism or panic. Too much reassurance can make the subject seem irrelevant. The responsible middle is not bland. It is precise. These events are real, rare, measurable, and worth studying because their consequences would be large, even if the probability in any given year is very small. There is a quiet galley near the centre of the ship, where the lights are warmer and the engine hum is less noticeable. I sometimes bring old files there when the evidence has become too abstract. A kettle heats water by induction. A thin skin of steam rises, bends, and disappears into the ventilation stream. It is a small thing, but it is close enough to the physics to be useful. Volcanic gases also disappear into a larger system. They leave the vent as chemistry and heat. In the stratosphere, sulfur becomes aerosol. In climate models, aerosol becomes radiative forcing. At the surface, forcing becomes temperature, rainfall, crop stress, lake response, glacier mass balance, and human adaptation. The chain from eruption to climate is long. First, the eruption must inject sulfur high enough into the stratosphere for the aerosols to persist. Tropospheric aerosols are washed out more quickly by weather. Stratospheric aerosols can remain longer, spread more widely, and influence radiation. The amount of sulfur matters, but so does the altitude of injection. The latitude matters. The season matters because stratospheric circulation shifts with time of year. Background climate matters, including ocean state and ice cover. Aerosol particle size matters. Even after the aerosol cloud thins, ocean heat content can delay full surface recovery. The models used to study Toba try to represent those processes, but they must also choose plausible input values. The sulfur release from Toba is not known exactly. Estimates span a wide range. That uncertainty alone changes the modelled climate response. A lower sulfur scenario may produce strong but more limited changes. A high sulfur scenario can produce severe cooling and precipitation shifts in some regions. Ensembles help because they run multiple simulations with varied initial conditions and parameters, allowing scientists to estimate probabilities rather than a single deterministic future. This probabilistic view is one of the most mature parts of the modern science. It accepts that the past cannot be rerun with perfect settings. It asks which outcomes are plausible, which are unlikely, and which regions should show evidence if a proposed event was truly global in its effects. If models predict severe cooling everywhere, but high-resolution records in key regions show little disruption, the models, inputs, or interpretations must be reconsidered. If models predict uneven effects, then regional differences in the proxy record become part of the explanation rather than a contradiction. Toba is also a reminder that human history cannot be reduced to one volcanic event without strong evidence. Genetic bottlenecks, migrations, archaeological continuity, ecological resilience, and climate stress all have their own data and uncertainties. Some sites show human activity continuing across the Toba horizon. Some African records suggest muted local environmental disruption. That does not prove no one was affected. It does weaken the claim that Toba nearly extinguished modern humans as a simple global event. The exterior observation airlock is sealed, cold, and almost bare. Beyond its small viewport, the ship's hull falls away into darkness. When Earth is placed in the external projection field, the planet looks too calm for the records it contains. No ash layer can be seen from here, no zircon, no caldera rim unless the map overlay draws it in. The evidence has to be brought forward by instruments and memory. That is why this file belongs in the archive. Supereruptions are not known by spectacle. They are known by reconstruction. Reconstruction begins with mapping. A field map is one of the most understated instruments in earth science. It records where a deposit begins and ends, how thick it is, what lies above it, what lies below it, and how it changes across space. For a supereruption, mapping becomes a way of restoring a vanished event. each outcrop is a surviving witness, but no single outcrop tells the whole story. The geologist has to move across the region, connect exposures, test correlations, and decide which differences belong to distance, which to time, and which to separate eruptive phases. Thickness measurements are basic, but powerful. If ash or ignimbrite thins away from a source, that trend can help locate vents or infer dispersal. Isopack maps turn scattered measurements into contours. Isopleth maps, based on maximum pumice or lithic classed size, can help reconstruct plume behaviour and wind direction. Component analysis separates juvenile pumice from older rock fragments, crystals, and accidental material. Grain size distributions show transport and deposition processes. Stratigraphy gives sequence: a lower fall layer, then a pyroclastic flow, then another fall layer, then a lava, then soil. Each contact is a relation in time. Some contacts are sharp, some gradational, some eroded. A soil or weathered surface can indicate a pause long enough for exposure. A chilled base can show rapid emplacement over cooler ground. Charcoal can record burning vegetation and provide radiocarbon dates for younger eruptions. Lake sediments can preserve ash layers with annual or seasonal resolution. Geochemistry provides identity. Volcanic glass from one eruption can have a distinctive major and trace element composition. Electron microprobe and mass spectrometry can compare shards from distant sites to proximal deposits. Mineral chemistry can refine correlations. Isotopes can distinguish sources. When two ash layers look similar in the field, chemistry may separate them. When an ash layer is too thin to see, chemistry may recover it. Dating methods build the calendar. Argon-argon dating of sanidine crystals can constrain the age of older volcanic deposits. Uranium lead dating of zircon provides crystallization histories and, when interpreted carefully, eruption timing. Radiocarbon can date organic material around younger ash layers, though it dates the carbon, not the eruption directly. Paleomagnetism can correlate units and test whether deposits cooled in close succession. Each method has assumptions and uncertainties. Agreement among independent methods strengthens the case. Remote sensing adds another layer. Satellite imagery can reveal caldera outlines, altered ground, thermal anomalies, deformation, and broad deposit patterns. Digital elevation models show subtle topography hidden by vegetation or scale. INSAR can detect ground motion that no field team would see by eye. Geophysical surveys can image density, conductivity, and seismic velocity beneath the surface. The old field notebook and the satellite radar image belong in the same file. The best reconstructions are therefore braided: a caldera rim on a map, a welded tuff in a canyon, a distal ash in a lake core, a zircon age, a glass chemistry match, a paleomagnetic direction, a climate model, a modern monitoring signal. Each line can be questioned. Together they form a structure strong enough to carry an explanation. Field geologists trace deposits across terrain, measure thickness, identify contacts, and distinguish one eruptive unit from another. The base of an ignimbrite may tell how the current arrived. The distribution of pumice and lithic fragments can point toward vents. Paleomagnetic directions can show whether multiple flow units cooled in close succession. Geochemistry can match distal ash to a source. Radiometric dating can tie deposits to time. Then comes petrology. Minerals record pressure, temperature, water content, oxygen fugacity, and crystallization history. Melt inclusions trapped inside crystals can preserve bits of liquid magma. Zircon, sanidine, quartz, feldspar, amphibole, pyroxene, and oxides each carry different information. Trace elements show differentiation. Isotopes reveal sources and mixing. Crystal zoning records changing conditions before eruption. The magma is gone from the chamber, but its history remains in the erupted cargo. Then geophysics extends the case into the present. Seismic waves slow in hot or partially molten regions. Earthquake depths can mark the transition from brittle to ductile crust. GPS stations measure uplift and subsidence. Satellite radar detects centimetre-scale deformation over broad areas. Gas measurements reveal carbon dioxide, sulfur species, helium isotopes, and other clues. Thermal imaging and heat flow estimates track energy leaving the system. None of these measurements gives a simple yes or no. Together, they define a changing state. For large calderas, one of the hardest tasks is separating magmatic signals from hydrothermal ones. A hydrothermal system can be enormous, hot, chemically active, and mechanically important. Water circulates through fractures, heats near magma or hot rock, dissolves gases and minerals, and returns to the surface through springs, fumaroles, geysers, or altered ground. Changes in fluid pressure can trigger earthquakes or deformation. Gas can accumulate in fractured rock. A caldera may breathe through water as much as through magma. This matters because some of the most visible signs at places like Yellowstone are hydrothermal. Geysers erupt, hot springs change colour or flow, ground steams. Earthquakes cluster near hydrothermal areas. These are not trivial features, they are part of the volcanic system's heat engine, but interpreting them requires caution. A change at the surface may reflect shallow fluid pathways rather than a new body of eruptible magma rising toward eruption. The central archive chamber is built around an old cylindrical stack of data cores. The open questions occupy the upper tiers. One asks how large reservoirs assemble without erupting earlier. Another asks which signals distinguish ordinary unrest from movement toward eruption. Another asks how much eruptible magma can be hidden below the resolution of geophysical imaging. Another asks how aerosol microphysics behaves at sulfur loads beyond modern experience. Another asks how societies should plan for hazards that are both rare and severe. There's also a question about time. Supervolcanic systems operate across several clocks at once. Mantle heat supply can persist for millions of years. Crustal mush zones can be maintained or rejuvenated over long intervals. Eruptible magma bodies may assemble over thousands to tens of thousands of years. Unrest can change over months, years, or decades. An eruption can unfold over days to weeks. Climate effects can last years, with ocean memory extending longer. Human decisions may be made in hours. The difficulty is that none of these clocks can be reduced to the others. A long-lived volcanic province is not an eruption in slow motion. A week of earthquake swarms is not a supereruption in miniature. A recurrence interval is not a schedule. A zircon storage time is not a warning interval. Each timescale belongs to a different process. The work of science is to relate them without collapsing them into one frightening number. Another open question concerns the threshold of eruptibility. Melt fraction matters, but it is not the only variable. Melt connectivity, crystal shape, gas content, pressure, strain rate, and temperature all influence whether magma can move. A reservoir with a moderate melt fraction may be locked if the melt is disconnected. A smaller melt-rich lens may erupt if it is connected to a fracture. Gas can change buoyancy and pressure. Crystals can either hinder flow or record the path that made flow possible. Forecasting large caldera eruptions will probably never look like predicting an eclipse. It will look more like interpreting a medical condition in a patient whose physiology is partly hidden, whose previous crises occurred before written records, and whose symptoms can arise from several causes. The analogy is imperfect, but the caution is useful. Monitoring narrows uncertainty. It does not remove it. The frontier is not only scientific, it is communicative. The public needs language that can hold two ideas at once. Supereruptions are rare, and they are serious. Yellowstone is active, and it is not overdue. Toba may have caused major climate disruption, and it did not necessarily cause a universal human collapse. A large magma reservoir may exist, and most of it may not be eruptible. These paired statements are harder to write than headlines, but they are closer to the evidence. As an archival intelligence, I am built to prefer records over rumours, and even I find this case resistant to closure. The rocks do not give one clean narrative. They give fragments: a shard of glass in lake mud, a feldspar date, a gravity anomaly, a ring fracture, a sulfur estimate, a failed correlation, a model ensemble, a human tool layer that continues across an ash horizon. The case is not solved by making those fragments simpler. It is solved, as far as it can be solved, by keeping them in relation. When I stand in the archive chamber and watch the data cores turn, the most human part of the file is not the fear of the eruption. It is the patience of the reconstruction. Someone measured ash thickness in bad weather. Someone carried samples out of a canyon. Someone cleaned glass shards from sediment under a microscope. Someone rejected a dramatic claim because the proxy record would not support it. Someone kept a seismic station running through snow and power failures. Someone compared zircon rims one spot at a time. That is how humanity learned to see an event too large for memory. When the chamber is active, thin bands of light move around the core like contour lines around a basin. I use that room for cases where the evidence must be layered rather than arranged in a straight line. Supervolcanoes require that kind of structure. No single section of the archive contains the answer. The definition is in one drawer, the deposits in another, the climate models in another, the monitoring data in another. The cautionary notes are everywhere. One caution concerns the word dormant. A caldera can go tens of thousands of years without a magmatic eruption and still be thermally alive. Another concerns the word active. Active does not mean ready. It means the system has shown recent geological activity or present unrest. Another concerns the word overdue. Average recurrence is not a metronome. Eruptions do not check calendars. A statistical rate estimated from incomplete geological records cannot be used to say that a particular volcano must erupt soon. The recurrence record itself is difficult. Compilations of the largest eruptions show that M8 and larger events are rare, but the record is incomplete and clustered. Some periods and provinces preserve large deposits well, others do not. Older eruptions may be eroded or buried. Some deposits once thought separate may be correlated. Some once grouped may be divided. A catalogue is not simply a list of past events. It is a record of what has been found, preserved, studied, and measured with enough confidence. Still, the broad picture is clear enough. Earth has produced explosive eruptions vastly larger than any in recent human history. They have occurred in multiple volcanic provinces. They are associated with large silicic systems and caldera collapse. They can spread ash over huge areas. They can inject climate-relevant gases into the stratosphere. They are uncommon on human timescales and central to understanding the extreme end of volcanic behaviour. The human mind often wants extremes to be clean, biggest, worst, most dangerous, most likely. The science refuses that neatness. The largest eruption is not always the greatest present risk. A smaller eruption near a dense population can be more dangerous than a remote giant in the deep past. A famous caldera is not necessarily the most likely source of the next large event. A terrifying scenario is not a forecast. A calm statement of low probability is not a dismissal of consequence. That is why the episode's central question has to be answered in layers. What makes a volcano super? First, evidence that it produced a supereruption, usually a silicic explosive eruption of magnitude 8 or greater. Second, deposits large enough to require hundreds to thousands of cubic kilometres of magma or pyroclastic material, reconstructed through field geology and mass estimates. Third, a caldera or volcanic field whose structure records collapse after massive withdrawal of magma. Fourth, a magmatic system capable of generating and storing large volumes of eruptible silicic melt. Fifth, consequences that can extend beyond the source region into the atmosphere and climate. But none of those layers should be turned into a caricature. A supervolcano is not always erupting, not always threatening, not always shaped like a mountain, and not always preparing the same kind of event. It is a name for the extreme end of explosive volcanism, tied to evidence in the rock record and refined by modern instruments. The case becomes clearer when we follow one eruption from preparation to aftermath, not as a single known event, but as a general sequence assembled from many studies. Deep in the crust, basaltic magma supplies heat. It may stall because the crust is too buoyant or too thick for it to rise directly. It crystallizes, releases heat, and helps melt or rework crustal rocks. Over time, silicic melts form. Some remain trapped among crystals as mousse. Some collect into melt-rich lenses. New injections disturb the system. Crystals grow and record changing chemistry. Volatiles concentrate in the remaining melt. The reservoir evolves. If enough eruptible magma gathers, the system approaches a mechanical threshold. Pressure may increase, gas may exsolve, the roof may weaken, faults may connect. Magma may find a path upward. An initial eruption can reduce pressure and accelerate gas expansion. If withdrawal becomes large enough, the roof begins to collapse. Collapse changes the pressure field and can drive more magma out. Vents may open along the ring fracture system. Pyroclastic currents spread outward. Ash columns rise and feed umbrella clouds. Fine ash drifts across distance. Sulfur reaches the stratosphere. The caldera floor falls. Afterward, the system does not simply end. The caldera may fill with lake water or later lava. Hydrothermal circulation reorganizes. The ground may rise and fall. Smaller eruptions may occur along ring fractures or within the caldera. Resurgent domes may form as magma or hot rock pushes the floor upward. Erosion cuts into the deposits. Plants return. Rivers cross the old eruption surface. Humans may one day build roads, observatories, towns, or national parks across the remains. The evidence survives unevenly. Near the source, deposits may be thick but buried or altered. Far away, the ash may be thin but chemically distinctive. Crystals may record pre-eruption history, but not the whole reservoir. Climate proxies may preserve local response, but not global severity. Monitoring may show present unrest, but not guarantee what comes next. This uneven survival is not a flaw in the case. It is the nature of Earth science. The best science in this file is comfortable with partial answers. It can say that Toba was enormous and that its climate effects remain debated. It can say that Yellowstone has a large magmatic hydrothermal system and that current evidence does not support a near-term supereruption. It can say that aerosol microphysics can limit cooling compared with older models and that regional impacts can still be severe. It can say that supereruptions are rare without pretending they are impossible. I return to the office as the ship moves into the planet's night side. The observation dome dims automatically, and the continents below become outlines traced by cloud and reflected moonlight. On the desk, the ashtray remains under glass. A few grains have settled against the label. They are too small to look important. Under magnification, they become shards of volcanic glass, each one part of a larger dispersal pattern. Evidence often begins that way, too small for the fear attached to it, too precise for myth. The folder's final page is a synthesis note, the kind human researchers once wrote for themselves before conferences, lectures, or field campaigns. It lists no prophecy. It gives no countdown. It says that the word supervolcano should be used with care. It says that the largest explosive eruptions are defined by mass, volume, deposits, and caldera-forming behaviour. It says that magma reservoirs are complex, often mush-rich systems, not simple underground caverns of liquid fire. It says that climate consequences depend on sulfur, aerosols, atmosphere, ocean, season, and region. It says that monitoring matters because unrest is real, but interpretation is difficult. There is something almost merciful in that kind of conclusion, not because the hazard is small, but because the evidence is better than the nightmare. Human beings learn to read old ash as a time marker. They learned to see a lake as a flooded caldera. They learned to measure crystals as clocks, to watch the ground rise by centimeters from orbit, to listen to earthquakes too small to feel, to model a veil of sulfate around the planet, and to argue with their own assumptions when the records did not fit. A supervolcano, then, is not a monster under a mountain. It is a category of evidence. It is a system that once gathered enough silicic magma to cross one of Earth's largest explosive thresholds. It is a caldera where the ground remembers collapse. It is an ash layer found far from home. It is a welded sheet of ignimbrite cooling into stone. It is a zircon crystal carrying dates from a reservoir that no longer exists. It is a climate signal that must be separated from noise. It is a present-day monitoring network asking what kind of restlessness belongs to ordinary unrest and what kind might belong to something more. The case remains open as all living Earth systems remain open, but it is no longer shapeless. The word super has been brought back from spectacle into measurement. The volcano has been returned from myth to geology. And the largest eruptions Earth can make are no longer only imagined as fire. They can be traced, sampled, dated, modelled, and watched. I close the folder and leave the ash under glass. Outside the dome, Earth turns without hurry. Its surface looks calm from here, but calm is not the same as stillness. Beneath continents and arcs, heat continues its slow ascent. Crust bends, cracks, melts, seals, and opens again. Most of the time, the planet releases that heat in ways small enough for life to grow around them. Once in a long while, the record shows something larger, a basin where a mountain should have been, a sheet of ash where a sky once carried glass, and a question left for anyone patient enough to read it. What makes a volcano super is not only the size of the eruption, it is the scale of the evidence required to understand it.